Hi, this is Tzvi Rosen, and today's lecture will be talking about Hilbert's Nullstellensatz. We spoke about this briefly at the end of the lecture on valuation rings, but today we'll give it our full attention and talk about its consequences for geometry. Okay, here's an outline of the talk. We'll start by discussing radical ideals and algebraic varieties. Then we'll show how the weak version of the Nullstellensatz implies the strong version. And finally, we'll look at two alternative proofs, one that involves Noether normalization, and the second that uses Jacobson rings. Okay, let's start by defining an affine variety. So let's say we have a ring which is a polynomial ring over a field. Okay. Then we can take any subset of this this ring. So, okay. Then we're going to define V. In particular, V of S. This will be the set of points P1 through Pn in the n-dimensional vector space over K, such that f of P, really f of P1 through Pn, is equal to 0 for all f in S. Okay, so no matter what polynomial I take in this set S, if I evaluate the polynomial on a point in V of S, it should come out to 0. And by evaluate, I mean wherever you see x1 in the polynomial, you put in p1, which is an element of the field. Okay. So that's V of S, and this is called the algebraic variety, or the affine variety, or the affine algebraic variety. Algebraic variety of S. Okay, going the other way, so you can think about, so this is one way to go from a subset of a ring to a subset of a vector space. In the other direction, if you have some subset of Kn, then you can define I of x to be equal to the set of polynomials in A such that f of P1 through Pn equals 0 for all P in X. Okay, so this is often called the vanishing ideal of X. So this is the vanishing. This is also called the vanishing set up here. Vanishing set, which explains the V notation. This is the vanishing ideal of X. Okay. So that gives us a way to go from an ideal to a subset of a vector space. And in the other direction, we have a way to go from a subset of a vector space to an ideal of a ring. Okay. And we'll give a couple of examples. So if I'm looking at, let's let P of X in K adjoin X be a polynomial in one variable, then the associated algebraic variety to this set is the set of roots in K for P of X, such that P of alpha I equals 0, alpha I in K. Okay. So that's pretty straightforward. So we'll get a finite collection of points in the field, in K1. Okay. Now let's consider a different the other direction, going from subsets of the vector space to ideals. So if you have the interval 0, 1 as a subset of, let's call it R2. Okay, so we're looking at, let's make it R1. Why not? Why overcomplicate? So then we're going to look for all of the polynomials which vanish at every point in this interval. However, if you have a polynomial satisfying that, any polynomial satisfying this, satisfying p of x equals 0 for any x in this interval, well, it would have infinitely many roots, which is strictly verboten for a polynomial. So that implies that the only eligible polynomial is the 0 polynomial. So v of x, where this is x, is going to be equal to the ideal, the 0 ideal. Okay, as a subset of Rx. Okay, and let's do one more. So if we were to take the let's take a semicircle. Okay, so this is going to be equal to the set of points x, y such that x squared plus y squared equals 1, and both x and y is greater than or equal to 0. Okay, so if this is our x, then the corresponding, oh, I'm sorry, this should have been the ideal of x. Then the corresponding ideal of this x would be the ideal generated by x squared plus y squared minus 1. So you can't really reflect the fact that y is greater than or equal to 0 in terms of an ideal of polynomials. That inequality doesn't quite translate into an algebraic condition. So it's as if we're just looking at polynomials that vanish on the entire circle. Okay. Let's look at a couple of properties of these maps v and I, sending a set to its sending an ideal or subset of polynomial ring to its vanishing set, and sending a set to the ideal, the vanishing ideal. So first off, if you have a subset v and w in your vector space, then the ideal associated to w is contained in the ideal associated to v. Okay? And you can think about it this way. If you have, so given f such that f of p equals 0 for any p in w, well, that includes, so because v is contained in w, that includes, so also true for p in v, because v is contained in w. So what this tells us is that the mapping I reverses inclusion. And the same is true going the other way. So given I contained in j in k adjoin x1 up to xn, the associated vanishing sets v of j will be contained in v of I. Why would that be? Well, if for any f, so take f in, or rather p in v of j, this is going to satisfy that f of p equals 0 for all f in j. But if that's true for any f in j, since I is contained in j, it's also true for any f in I. So we've got this correspondence between varieties and ideals, where containment of varieties in one direction translates into a containment of ideals in the other direction. And this should hopefully be kind of making you curious. I wonder if there's some type of bijection between ideals and varieties. The answer is not quite, but it's made correct. That statement is made correct using Hilbert's Nullstellensatz. So if we let K be an algebraically closed field, and I contained in K adjoin x1 through xn is an ideal, then I of V of an ideal I is equal to the radical of that ideal I. So this is our map giving the correspondence, and I is a specific ideal. Okay. So let me briefly illustrate why it's important that K is an algebraically closed field. So for example, so K not algebraically closed means that you can have functions that, you can have ideals that are not equal to the whole ring, that aren't equal to the unit ideal, but they have this, that they don't have any points that vanish. So for instance, if we look at the ideal x squared plus y squared plus 1 in as a subset of R adjoin xy, so this ideal, the variety associated to this is a set of real points where the functions in this ideal vanish, but there are no such points because that would require a sum of squares being equal to -1. So this is equal to the empty set, but then the ideal of the empty set is equal to the whole ring because by vacuous, the statement that any polynomial in this ideal vanishes on all points in the set is vacuously true. So we get the unit ideal. So that's why we have to be careful about algebraic closure. But once we have algebraic closure, this statement is, what this statement tells us is that, so the consequence, there's a one-to-one correspondence between radical ideals and algebraic varieties. Which is pretty cool. That tells us that we can understand algebraic varieties just in terms of the radical ideals of a ring. Okay, well, you might be curious at this point. Oh, and this is a picture of Hilbert, David Hilbert, one of the titans of mathematics. And he proved the Nullstellensatz first using techniques from elimination theory. So the proofs we'll see today are not do not reflect the way that Hilbert proved his Nullstellensatz. But you might be saying, wait a second, this version of the Nullstellensatz doesn't look anything like the version we saw in the last lecture, which was if we have K a field and B a finitely generated K algebra, then if B is a field, it is a finite algebraic extension of K. That has nothing to do with ideals and varieties, seemingly. And you'll recall we proved using results on valuation rings extending homomorphisms. Extending homomorphisms into algebraically closed fields. So how can we turn this statement about a certain K-algebra being, if it's a field, then it's a finite algebraic extension field. How can we turn that into a statement regarding varieties and ideals? Well, the first thing we should note is that this is equivalent to the weak Nullstellensatz. The weak Nullstellensatz is as follows. Let K be an algebraically closed field, and I, contained in the polynomial ring and n variables, be an ideal satisfying V of I equals the empty set, then I is equal to the whole ring. Okay? So how would we prove this using the statement here? Well, suppose not. Then I must be contained in some maximal ideal. And if we have the ring B equals K adjoin x1 through xn mod m, this is going to be an extension field of K. But as we saw, when you have a field which is an extension field of K, that tells me that B is a finite extension field. And if B is a finite extension, or in other words, an algebraic extension, that means that it has to be equal to K because K is algebraically closed. So any root that you would adjoin to a polynomial is already in there. So that implies B is isomorphic to K. Well, once B is isomorphic to K, that means that we can consider how the quotient field acts as an isomorphism. So that means that the quotient map has kernel 0, or has kernel m, exactly kernel m, with no extra stuff picked up. So that means that we can consider in particular where all of the elements are mapped to. So xi will be mapped to, let's say, ti in K. So that means that the maximal ideal will have kernel precisely given by x1 minus t1 up to xn minus tn. Okay, it's not hard to check that this is, well, okay, strictly speaking, this really should be said to be contained in here, but we know that this is maximal, so that means that this really should be an equality. So by virtue of this map from B to K being an isomorphism, we can see what values xi takes there, and that proves that the maximal ideal has to contain this other maximal ideal with very specific formulation. But then if this is equal to m, then that means that the set given by t1 through tn vanishes on all polynomials in I. Okay, so t1 through tn must be in V of I, sorry, which is a contradiction. Okay, so that tells me that the ideal associated to the empty set must be equal to the whole ring. Okay? That's the weak Nullstellensatz, right? Because the strong Nullstellensatz, the full Nullstellensatz, makes a statement about how v of I of v, rather, I of v of I, is equal to the radical of I. So we've got to see how we can get there from this weak version. Okay, so we were able to get from our result last lecture about valuation rings to the weak Nullstellensatz. Now we want to get from the weak Nullstellensatz to the strong Nullstellensatz. And for that, we'll use the Rabinowitsch trick. So we're going to take as granted that if I of v is equal to, or rather, if v of I is equal to the empty set, then I is equal to the whole ring. And we want to prove that I of v of I equals radical of I for any I in this polynomial ring. Okay, so the structure of the proof is as follows. So consider, so take f such that, take f in I of v of I. That means that this f of p is equal to 0 at all the same points as the functions in I. Okay. So suppose that we extend our ring. So we add in a new variable y. So we'll take I prime to be equal to I, but then adding in one new generator to our ideal, specifically f times y minus 1. And this is going to be taken as an ideal in k adjoin x1 through xn and y. Okay. So examining this ideal, you can convince yourself pretty quickly that v of I prime is going to be empty, right? Because if you specialize the variables x1 through xn to something that vanishes on everything in the ideal, in the ideal I, then we know that it'll also vanish, that the function f also will vanish, which means that fy minus 1 will never be 0, because in order for that polynomial to be 0, that means that f must be invertible, which means it can't be 0. So y for p in v of I, then when you let's actually make this a bit clearer. For p1 through pn in v of I, that means that f of p1 through pn equals 0, which means that fy minus 1 is not equal to 0. And if you have p1 through pn not in v of I, then that means that there's some g in I such that g of p is not equal to 0. Okay, so whether you're inside of v of I or outside of v of I, you're going to be, and let's make this gpy is not equal to 0, and it doesn't matter really what the y is. Okay? So that should convince us that this v of I prime is indeed the empty set. So if we know from the assumption that we're making with the weak Nullstellensatz, that if v of I is empty, that means I is the whole ring. So that means that I prime is going to be the whole ring. Okay, and when you have the whole ring, that means in particular that the unit is in your ideal. So that means that 1 can be expressed in terms of generators of our ideal, but that means that it can be written as some collection of polynomials in x1 through xn and y times some element in the ideal, some generator of the ideal, let's say, fi of x1 through xn, where I goes from 1 to, let's say it's k. And then we also pick up some polynomial q of x1 through xn y times fy minus 1. So what does this give us? Well, it gives us a polynomial in y's, in x's and y's, but we want a relation that involves f that doesn't involve y, because it should take place in our original ideal. So what we'll do now is specialize y equals 1 over f. Once you specialize y equals 1 over f, what you have is still 1 on the left-hand side, but then with this sum, all of these coefficients are now polynomials. Oh, and this probably should get an I. These are now polynomials in x1 through xn and 1 over f times fi over x1 through xn. As for the second term, that vanishes altogether, right? Because f times 1 over f minus 1 equals 0. So what does that mean for us? Well, because these are polynomials using all the permitted variables, but then also 1 over f, all of these will have denominators given by some power of f. But then we can clear denominators, which means that f to the m will be equal to some collection of polynomials qi of x1 through xn times fi of x1 through xn, which means in particular that f is in the radical of I. Okay? And that's the Rabinowitsch trick. It's basically just localizing at f, but I think this presentation captures something nice about being able to clear denominators and then finding magically that your polynomial is in the radical. Okay, so now we've proven that the weak Nullstellensatz implies the strong Nullstellensatz, and since we showed the weak Nullstellensatz using the valuation ring techniques from last week, last lecture, that gives us the Nullstellensatz. But now we'll look at a couple of alternate proofs, starting with a proof that works via Noether normalization. This is Emmy Noether. She was one of the greatest algebraists of the 20th century. This is a technique she developed to prove the Nullstellensatz. It's the Noether normalization lemma. If you have K an infinite field, and this is not a necessary condition, except for this proof. Okay, there's another slightly more complicated proof for fields that are not infinite, but this proof is a little cleaner, and it just relies on the fact that it's an infinite field. So if we have A not equal to 0, a finitely generated K algebra, then there exist elements y1 through yr in A which are algebraically independent over k, and such that A is integral over k adjoin y1 through yr. Okay, so just to visually depict what's going on, we have k, y1 through yr, and A, and so this is a transcendental extension. In particular, none of these have any algebraic relations, and this is an integral extension. Okay, and we've seen all of the really nice properties that integral extensions have, particularly in geometry. And so we're saying that this can always be done for a finitely generated K algebra. Okay, let's prove it. Okay, so suppose A equals K adjoin x1 through xn. Okay, obviously these must exist because it's finitely generated. And some subset of them are going to be algebraically independent. And you can actually show that that the size of the largest set of algebraically independent values here doesn't depend on which you choose to start. Right? You can use a greedy algorithm to get a set of the maximal size. So we can choose our algebraically independent elements. So we just by relabeling. So renumber x1 through xn so that x1 through xr are algebraically independent. Okay, and that the rest are algebraically dependent on the first few. xk is algebraic over k adjoin x1 through xr for all k greater than r. Okay, so that should be doable. And now the plan is as follows. So we'll work by induction over on the number of additional variables we have. So induction on n minus r. Okay, so if n minus r equals 0, then clearly this is already, then we're already done, because we don't have any elements, so all of the elements are integral. Fine. So suppose that it's true for n minus r equals k. We want to show that it's true for k plus 1. So if we're adjoining k plus 1 additional variables, we should be able to find the last one integral as well. Okay. So suppose, so by the induction hypothesis, k adjoin x1 through xn minus 1 is integral over k adjoin x1 through xr. Okay. And we want to show that xn is also integral over k adjoin x1 through xn minus 1. Okay, so xn must satisfy an algebraic, a polynomial relation xn equals 0 So this won't necessarily have a power of xn, the highest power of xn on its own. It might have a coefficient. But if we can take the highest degree part of f, so take the, let's say this is degree m, so we can take the degree m part, of f, let's call it fm, and we can take a point, lambda 1 through lambda n minus 1 together with 1, which such that this fm is not equal to 0. Okay, and this is where we need the infinite field. We need to know that this this is possible. All right, and if you have an infinite field, then the finiteness of the number of roots of a polynomial will tell us that you'll have many points where this is not equal to 0. Implies this is okay. And what we're going to do is set x1 prime, or xi prime, equal to xi minus lambda I xn for all I less than or equal to n minus 1. And then the result, so take it, then xn will be integral over the xi primes. Okay? So in particular, the polynomial that we had before, f of x 1 through xn equals 0, implies that f of x1 prime plus lambda 1 xn, right? Because that's the same thing as x1. That's the same thing as x1, up to xn minus 1 prime plus lambda n minus 1 xn, and xn also equals 0. Okay? That's just by identifying those two expressions. But then this polynomial, in terms of what its highest degree term is, so every monomial will give us some x to the n, and the fact that x will give us a power of x to the of xn, and the fact that this polynomial fm doesn't vanish tells us that that term won't be cancelled. Implies highest power of xn appears on its own without coefficient. So the ring A, which we are interested in from the beginning, x1 through xn, this is going to be integral over this A prime, which is k adjoin x1 prime up to xn prime, xn minus 1 prime, apologies. But we already had, we had assumed by the induction hypothesis that algebras generated by n minus 1 elements are going to be, will satisfy this Noether normalization lemma, which will tell us that there exists y1 through yn minus 1, so that A prime equals k adjoin y1 through yn minus 1, satisfying the conditions of the Noether normalization lemma, and so, and in particular, this is integral over k k adjoin y1 through yr. And an integral extension of an integral extension is integral, so that means that a is integral over k adjoin y1 through yr. Okay, so that's Noether normalization. In terms of a geometric interpretation of that, so we'll recall that integral extensions relate to surjective maps with finite fibers. Okay, so when we're saying that, or the way that the proof just worked, we said that basically we can find k adjoin y1 through yr, so that tells me that there is an r-dimensional subspace of Kn and there's a linear transformation which surjects onto that subspace. Let's call this L, such that the affine variety with coordinate ring A and this is just equal to k adjoin x1 through xn mod I of v. Okay, so it's the affine variety of v. Surjects onto L. Okay. So it might be helpful to see a specific example of this. So we can think about the algebra k adjoin xy mod xy minus 1. And we saw when we did integral extensions, this is not actually an integral extension because when you look at this, that's not pretty. One more try. Okay. There's going to be one point here which it is not surjected onto. Okay, and the way that Noether normalization corrects that in the proof that we just saw is we say, okay, so certainly x, this is algebraically independent. Then when I add in y, this is algebraically dependent on k adjoin x. So now we're going to try to put in a change of coordinates, using this this shift. So we know that xy minus 1, the highest degree part of this polynomial is xy, and we know that if I, for instance, take lambda 1 here to be equal to 1, then the polynomial x minus 1 times, or rather xy evaluated at 1, 1, xy evaluated at 1, 1 is not equal to 0, it's equal to 1. So I can plug in x prime equals x minus y, and then k adjoin x prime y satisfies the conditions of the Noether normalization lemma because we have y is the equation xy minus 1 equals 0 translates to x prime plus y times y equals times y minus 1 equals 0, or y squared plus x prime y minus 1 equals 0. Okay, now this is a monic polynomial, so it gives us that y is integral over k adjoin x prime. Integral over k adjoin x prime. geometrically, what's going on? Well, we're saying, so x minus y is the linear subspace that we care about. So in particular, I think that would signify this line. And if we take, so obviously there's, this is again related to the fact that this is not, this is a picture in R2, so it looks like we have empty fibers here, but really we don't because everything is complex. So this should be the complex numbers. So we're going to ignore this. But for most, for certainly all complex points, what we'll have is when we project down onto this image, we have 2 points in the fiber. Okay? And that tells me that this is an integral extension, which will be surjective. Okay, so that's Noether normalization. And how can we show that Noether normalization implies the weak Nullstellensatz? And you'll pardon the vowel omissions here, but those are some long words. Recall again that the weak Nullstellensatz states that if K is an algebraically closed field, and I in K adjoint x1 through xn is an ideal satisfying V of I equals the empty set, then I is the whole ring. Suppose not. Then we have some maximal ideal containing I. Okay. And if we take A to be K adjoint x1 through xn mod m, this is going to be equal to K adjoint y1 through yn, where the first string is algebraically independent and the last string is integral. But because the whole extension is algebraic, that just means that all of these are integral over K. This means that you should be able to send yi, so there will be yi can go to alpha I, a root of its defining polynomial. Over K, which means that we will have a point that where everything in the ideal vanishes. Where all polynomials in M vanish. And since I is contained in M, everything in I will also vanish there. So it's impossible that V of I is the empty set. So that's the contradiction that we were looking for. And we conclude that, that the ideal must be the full ring.